Right, here we go. We're going to do 18.1 and 18.2 together on this one. So starting at page 478 here. So this is a picture basically in Fort Lauderdale. Big storm surge, so basically they're bulldozing the sand back onto the beach because a big storm surge occurred and pushed a bunch of sand onto the boulevard. So when this is happening more and more and more often in southern Florida, Miami Beach in particular about this, kind of an interesting central case study, talking about with rising sea levels. In Miami, there's a ton of businesses and tons of money literally meters away from the ocean. So, see our dynamic culture. So what is climate change? So the big thing I want to point out here is this diagram. It's basically going to be, this is page 481. So the yellow is basically the incoming. You can see a total of 340 units are in watts per square meter. So 340 watts per square meter are coming in. So you can see absorbed by the atmosphere, some is reflected back, some of them comes back and reflected by the surface, some is absorbed by the surface, and so on. So that's all the incoming stuff. Now the outgoing, basically it's turned into long wave radiation rather than just short wave solar radiation. It's changed when it comes out. So either it's emitted by thermals, evaporation, stuff like that, or it's called back radiation, which basically greenhouse gases capture some of it and push it back down to Earth. And this is the greenhouse effect. Basically, a bunch of stuff coming in, a bunch of stuff getting reflected out, but this kind of captures it and helps warm our planet some. This is the greenhouse effect. It's back radiating or pushing the heat back down to the Earth. All right, so there's two sticky notes here. So the first one is pretty straightforward stuff. So climate is long term, weather is very short term. So there's things called global climate change or global warming. This is kind of all the same general trend is what we're talking about. There's different names for it, but this is kind of the overall kind of the Earth is warming over time is what they're talking about over here. So now there's three parts of the climate. So there's the sun, there's the atmosphere, and then there's the ocean. So they absorb about 70% of the sun's energy, and the other 30% is simply reflected back into space. Or, like we saw down here in the bottom, some of it is emitted back in because of the greenhouse effect and the greenhouse gas in the atmosphere. So if we increase the greenhouse gases, the back radiation is increasing as well. Moving to 482 here. So as the Earth warms, it emits infrared radiation. Then the greenhouse gas absorbs it. We're talking about water vapor, ozone, carbon dioxide, nitrous oxide, and so on. The methane is the CFCs we just talked about last time. The greenhouse effect is good, but it can get out of hand very quickly. Because like I talked about, capturing the sun's energy to warm our planets, that's a good thing. But if we absorb too much of it, that's when it starts getting out of hand. So this picture up here, figure 18.3, shows basically the carbon dioxide, methane, and nitrous oxide. Basically, you can see how stable it was, and now it's just skyrocketing is what's going on. So moving to 483, aerosols tend to cool the climate. So these are microscopic droplets of particles. They can either have a warming or cooling effect. So soot particles, black carbon, aerosols, those are good things that warm the planet. The sulfur dioxide is part of the aerosols that reflect the sun's rays. Basically kind of pushed it back out to outer space like I was talking about. Now volcanic eruptions can cool the climate because of that sulfur dioxide. So if you stick a whole bunch of sulfur dioxide in the atmosphere, it reflects a bunch of it back into space and it cools it down. There's also a thing called a radiative forcing. Now this is the amount of change in thermal energy that the factor causes. So, volcanic eruption pushing a bunch of sulfur dioxide. So the amount of change in thermal energy, this basically is going to be a change in the negative because it's going to cool us down. Does that make sense? The amount of change in thermal energy that the factor causes. So thermal energy is heat. If the sulfur dioxide pushes more heat away, it's going to be a negative radiative forcing. Now the diagram here, 18.5, talks about total anthropogenic radiative forcing. You can see how much basically a lot of it's going on. So we have more carbon dioxide. That's a positive or a plus in the radiative forcing.
the halocarbons, methane and nitrous oxide, the ozone as well. The soot on the snow, that's the thing that's kind of pushing it back. And land use is cooling. Aerosols are cooling or going to negative. But the net with all of it is a very, very, very high positive, unfortunately. All right, moving to 484. Positive and negative feedback loops. And we've talked about these before, but just kind of like to put it into kind of some examples. So you got a positive feedback loop. So the temperature increases, therefore more water is going to evaporate, and then therefore it can hold the sun's energy, which means the temperature is also going to increase. But on the flip side, the negative feedback loop, temperature increases, the water evaporates, therefore the water changes into clouds, and the clouds reflect it, then the temperature goes down. This is the big change right here. The water evaporates, it either can turn into clouds to reflect it, or it's just going to stay kind of not condensed together, and it's just going to hold the sun's energy. That's the big difference between positive and negative feedback loop. Now, there are some natural climate variations. Okay, a thing called the Milankovitch cycles, which I'm going to talk about on the next page, but I want to show you this diagram real quick. So it talks about there's an axial wobble. Basically, you can see kind of this moving back and forth a little bit. The variation of the tilt between 25 and 22 degrees. But there's also how we can basically go from a really oval shape to a more circular shape as well. So, like I said, this is what I put on the sticky note here, the natural climate changes. So the Milankovitch cycle is the tilt of the Earth. The orbit is not perfectly circular, so therefore there'll be some months where we're literally closer to the sun than others. There's also solar output. That actually doesn't change very much though, comparatively. Then there's ocean absorption, absorbs CO2 to slow climate change. We've talked about that a bunch of times. The ocean absorbing a lot of the CO2 that we're producing. And the ocean circulation transports heat to the poles. We've also talked about that. You know, like how Europe is so much warmer than its latitude equivalent in North America. There are also things called proxy indicators. So this is indirect evidence of different events, such as a drought, fire, a wet year, atmospheric conditions, types of vegetation, etc. So they can be core samples, tree rings, coral samples, a few examples. So you can see the picture in 1807, they're taking ice sample cores, is what they're doing there. And one of the things, talk about the ice cores, is this next page here, this science behind the story. What can we learn from the world's longest ice core? So you can see right here, they drilled down 10,728 feet to bedrock and pulled up more than 800,000 years worth of ice. That's really important because the ice is going to basically take kind of like a snapshot of the climate that year, and so they can analyze it over time. So this is what they came to figure out. So years before present, you can see we're basically present years right here, basically going back, so 800,000 years ago. You can see you got temperature change, and this is relative to what we are at. So think of us like currently we are at 0. And so you know it goes down to -8 degrees, +4 degrees, and so on. Then you can see the methane, you can see the amount of carbon dioxide, and you can see that basically it's almost a mirror image. When the methane goes up, temperature goes up. When the CO2 goes up, temperature goes up. So they're almost, all three of them are almost mirrors of each other the whole time. Right now, there's the carbon, there's methane. And so like, you can kind of like predict where our temperature is going to go based on the past history of CO2 and methane, their levels mimicking the temperature change in the climate. So moving on to 488, it's going to be the last one for this one. So he's talking about we have accurate temperature, wind, rain, and sea ice formation data for the past 100 years or so, but predicting the future, this is done by climate models. Now, one of the things they do is actually in Mauna Kea, Hawaii, the big mountain in Hawaii, they take samples, atmospheric concentrations of carbon dioxide are rising steeply. So you can see the monthly trend, the monthly mean or the monthly average versus the trend. So you can see just, what was that, 70 years ago, excuse me, 80 years ago, it was way down here. Look how high the atmospheric concentrations of CO2 are right now. That's what we're talking about, the trends over time. And so looking back to kind of analyze how those trends have caused the temperature to change,
That's what we use in those climate models.